So we left our hero wrestling with bonding and the different bonding styles it's sometimes called, and learned that there essentially are two ends to sort of this continuum of gain, losing, or sharing electrons. Ionic bonds forming when the electrons are transferred and the positive and negative charges then attract all the ions together. Covalent bonds forming when the electrons are shared. In the previous video, we talked about the differences in electronegativity, and here all I'm going to do is illustrate the use of our decision rule to classify some bonds. And you might ask, well, why do we care what kind of bond it is? Well, the type of bond is going to heavily influence the physical properties of the substance, and you remember that tailing all the way back to the beginning of the class. It is those properties, that explanation for what the properties of various substances are, and the prediction thereof is very, very central to the theme of chemistry. Consider what's happened between two hydrogen atoms as they get together. Remember that hydrogen, of course, group 1, period 1, has one valence electron in its outer energy shell, the 1s shell. That period 1, in fact, contains only a single s shell. 2 electrons can fit in that shell. And so as two hydrogen atoms approach each other, the nucleuses of the nuclei, I guess, of each of those is attracted to the electron of the other. And as we'll see, because the two electronegativities are exactly the same, neither hydrogen atom is going to get that electron more of the time. The two 1s shells overlap, and we can actually sort of draw what those look like. They're equal, they're identical, and we end up with a single, we call it, covalent bond that forms between those two that is perfectly nonpolar because of the equal electronegativities. It's also important to remember that any time a covalent bond forms, we're talking about a molecule, and hence we write the formula for a molecule of hydrogen as H2, the subscript telling us we have 2 hydrogens in this molecule. I'll have a lot more to say about, obviously, chemical formulas as we get down the road, but for now we just remind ourselves that whenever electrons are being shared, the unit of interest is this molecule of H2. H doesn't exist in nature because in any concentration of note, the two H's will find each other, overlap their 1s clouds, and form that covalent bond, so that in nature, H2 is what it forms, and that's why we write hydrogen almost invariably as H2 to recognize that that's how it's going to be found in nature. Consider the difference between hydrogen and chlorine, and we already did this before, and I'll just reinforce that drawing here. Obviously, hydrogen has that 1 valence electron, right? Just for fun, I'll put chlorine up there in a different color. Has those 7 valence electrons. We talked about their status, 2 of them in that 3 s cloud, 5 of them in the 3p cloud, and so as the 2 then atoms approach each other, notice that hydrogen needs 1 more electron to complete its valence shell of 2. Chlorine needs 1 more electron to complete its valence shell of 8. But the difference between chlorine and hydrogen is only about 0.9 in terms of electronegativity, which is not enough to strip that electron out of the 1s shell of hydrogen. And so the thing that happens here is that the hydrogen and chlorine work out this sharing arrangement whereby that electron then is jointly owned by the chlorine atom and the hydrogen atom. We have, again, a molecule glued together by a single covalent bond. And HCl then is the formula for hydrogen chloride. We'll talk a lot more about naming in the next chapter, I believe. And away we go. The only difference here between this and H2, however, is that the greater electronegativity of chlorine means that it is going to have a higher electron density around it than hydrogen. Another way of thinking about it is sort of a partial ownership. That is to say, chlorine has that electron more often, or it's closer to chlorine, or however you want to think it through, which produces what we call a partial charge on both of the players. That is to say, because chlorine is more electronegative than hydrogen, it ends up with a partial negative charge on its end, whereas hydrogen ends up with a partial positive charge. These partial charges are not the same as full unit charges that ions have, but nonetheless, we say that hydrogen chloride is a polar molecule because the end with the chlorine is going to have a partial negative charge, and the end with the hydrogen is going to have a partial positive charge. And that polarity is going to have a huge effect on how hydrogen chloride molecules interact with each other. Finally, we'll consider the difference between lithium and fluorine and talk about what's happening here. And you've already seen this as well when I did that introductory thing. The electronegativity of lithium is about 1. The electronegativity of fluorine is 4. Fluorine is the highest electronegativity, has the greatest ability to attract electrons to it in compounds. Makes sense. It sits there up in the upper right-hand corner of the periodic table. And as a small atom with 1 electron short of the full valence shell, and hence it has a powerful ability to draw electrons to it when bonds are formed. In this case, the difference between the electronegativities is so huge that we, in a sense, concede the electron to fluorine. Remember that it's harder to draw this using our diagram because the electron from lithium is essentially given over completely to fluorine. How do you want to show that here? I'll just show it like this, install it here, and as a result, that electron is now gone. Lithium now is isoelectronic with helium, meaning it now has only 2 electrons, a full 1s shell, and has a positive charge. A full positive charge, which perhaps I should begin to write to distinguish them from partial charges. Fluorine has sole possession of lithium's valence electron, and so it now has a negative charge, and because the positive and negative charged ions have a strong attraction to each other, they come together and make a bond, an ionic bond, which will result in a crystalline solid with alternating lithium and fluoride ions, and we call that substance LiF. But it's important to see now and keep in your mind that this is not a molecule, and in fact, this formula does not imply there's just 1 lithium ion and 1 fluoride ion, but rather it is what we call a formula unit, which is a formula that describes the ratio between cations and anions. And by tradition, we write that so that the formula unit is neutral. If lithium has a charge of +1, fluorine has a charge of -1, then 1 lithium and 1 fluoride produces then a neutral formula unit, LiF. Not only that, the formula unit and the ratio between cation and anion essentially controls the crystal structure that the ionic compound develops. And so that's good. This is a chemical formula, but it is not a molecule. Molecule restricted to the formation of covalent bonds. You say, do I have to go through all this thing and remember electronegativities and do all this calculations? Sometimes. But simply put, if you study your trends in electronegativity, you can see that anytime you're dealing with a metal on the left-hand side and a non-metal on the right-hand side, the difference in electronegativity is going to be huge. And very likely, so big that the electron will transfer to the non-metal and we will form an ionic bond, and that substance would have ionic properties. And you're going to talk about what those are, and you're in fact going to sort of explore that in a lab. On the other hand, anytime 2 nonmetals get together, typically they already both have high electronegativities or decent electronegativities. And as a result, they won't be able to exchange electrons. No one's going to grab it, no one's going to keep it, no one's going to steal it. And that covalent bond then forms as a result of that lowering the system energy and the sharing of the electrons. If the two nonmetals are identical, like hydrogen and hydrogen, then obviously that sharing will be pure and nonpolar or equal. But we can essentially conclude that anytime there are different elements involved in that sharing, that there will be some degree of polarity to that bond. And obviously then the degree of polarity is going to relate to the difference in those electronegativities. And the greater the difference in electronegativities, the greater the polarity of that covalent bond. And it makes sense, doesn't it, that if the difference in electronegativities gets so great that the metal gives up the electron, the nonmetal takes sole possession of it, and now the strong unit charges cause the ionic compound to come together. So once again, we have a continuum of bond character depending upon that all-important electronegativity.